Okay, so the recording is started, and I just want to welcome you all to tonight's session of OTF Connects, titled Empowering Students Through Sense-Making in Mathematics with Laura Ginny Newman. We have a very large group tonight with mostly experienced users, and many of you already know Laura. You know that she's also one of our most experienced facilitators, so I'm sure that it's going to go very, very smoothly. Je voudrais profiter de l'occasion pour souhaiter la bienvenue à tous nos collègues franco-ontariens. Cette session sera en anglais, bien évidemment, mais si vous avez des questions en français, surtout n'hésitez pas à me les poser par la suite, soit dans la boîte de chat ou par email. Et à la fin de cette présentation, je vais aussi parler, parce qu'on a une session en français demain soir, et je vais en parler également. We're definitely thrilled to have each and every one of you with us tonight, and it's an absolute pleasure to welcome Laura Ginny Newman. Laura is a member of the Critical Thinking Consortium, also known as TC Square. She's currently working on the development of a number of resources to support the implementation of critical thinking in the teaching and learning of mathematics. She has been a teacher for over 20 years in secondary and post-secondary level. And she's one of Ontario's most renowned experts on critical thinking and one of our most regular presenter on OTF Connects and on many other OTF events. So anyway, we are fortunate to have Laura with us tonight. And Laura, so at this point, I'll pass the microphone to you, and I'll let you take over to present your tonight's presentation. Just remember to click on your talk button when you're taking over from me, and then you can go ahead. Laura, I don't know. Okay, hi. Perfect, excellent. Okay, thank you.
Thank you. Good evening, everyone. I'm going to start us all over again, and I apologize for jumping in too quickly. There was a pause, so I thought it was an opportunity to get started. Thank you for joining us this evening. I am so always deeply appreciative of people who take some time for professional learning in the evening after they've had a full day of work. So thank you so much for joining us, and thank you so much for joining us to spend some time talking about the teaching and learning of mathematics. I want to start off our session today asking you just very quickly, so that I have a sense of who's in the room this evening. What grades are you teaching? If you can quickly just put in your chat box the grades that you are currently teaching, so that I can get a sense of who's in the room. Thank you very much. That's fabulous. We have such a wide range of teachers from different grade levels. It's fabulous. I think it's you'll find that no matter what grade level you teach, thinking about sense making in math is going to be relevant to the work that you do. I have chosen a few examples for us to work through tonight, and some ways of engaging us in the thinking that's required for sense making. So I apologize if not every grade level is represented, but hopefully you'll see something that's of relevance to you this evening. I want to start off by just talking a little bit about sense-making and why such a session and why sense-making is such an important topic of conversation in math. And I want to start here by just referencing some research that was done, research that I think is really quite powerful, and there's a web link there for you to take a look at. But basically, research that says that both decision-making and sense-making in math classrooms are what intrinsically motivate our students in classrooms, and not only deepen their understanding, but build their capacity to be able to work with any mathematical ideas or concepts that they're learning by enforcing and helping them develop their reasoning capacities. And if you have an opportunity to take a look at this research paper, I think you'd find it quite interesting, and how they've gathered the research and how it supports this work. I also want to talk a little bit about just introducing to you some questions. These are probably questions that, for the most part, you ask almost every day in your classroom. They're widely used questions in math classrooms, and they're also widely promoted all the way around the world. So these are probably very familiar to you. Things like, what does this or that make sense? Is it reasonable? How do you know? What will happen if? Is it always true? What's going on here? And I just want you, given the nature of those questions, I want you to think about whether you can come up with any other questions that you've used in your classroom that invite your students to engage in some sense making, or get them thinking about the nature of what it is that they're doing, how deeply they understand it, and if it's reasonable and brings meaning to their learning. So just very quickly, if you want to just put in the chat box, can you think of any other questions that you might use? Can you prove it? Absolutely. How would you explain this to a partner? How do you know the answer is right? Give me a real-world example. Can you represent this in another way? Or how many other ways can you represent this? Why do you think this? How do you know your answer is wrong? Fabulous questions, and all questions that are inviting your students to pause and take a moment to think about what it is that they're doing in their math classrooms, as opposed to simply plugging along and just continuing to move forward without being reflective about what it is that they're doing. And important questions for you as teachers to make sure that you can gather that really, that evidence of learning from your students to see what they're really understanding or what they're not understanding. So great questions. I would like to just share with you some others. And I want to highlight something that's really important about the nature of questions that we ask, because if you remember the slide that we started off with in the research, it suggested the idea of decision-making and sense-making, and that there's a relationship between the two. And one of the things that we really want to think about as we invite our students to engage in sense-making is getting them to not only reflect on what it is that they're doing, but also reflect on the quality of the way in which they are doing things. Surfacing thinking in our math classrooms is really important, but even more important is making sure that the students understand what it means to engage in really good thinking and quality thinking, because that's the thinking that's going to ultimately lead to their success in their math classrooms. So you'll notice here that there's a series of questions, and they look slightly different, but what I've done is I've bolded some words here that really tend to provide qualifiers that get to the quality of a student's thinking. And they're qualifiers that also very explicitly invite students to engage in decision-making in their math classrooms. So you'll see words like most likely, so what's the most likely solution, conclusion, and then we tend to use this word when we want our students to engage in conjecturing or to estimate. You'll see, does this relationship, this solution, whatever you're doing, is it reasonable? Does it make sense? And that's ultimately asking them also to make a decision. Have you done this? Have you proved this? Often we ask students, can you prove this? And that's really important, but we really want to get to the quality. So can you prove this in a logical way? Can you prove this in a way that really gets to the quality and the nature of the thinking that you're doing? When we ask students to justify their answers, solutions, conclusions, we often do that, but we don't very often talk about if they've effectively done that. What's a good justification look like? And is their form of reasoning or thinking appropriate given the nature of the task or the question? So all of these things are really important, and you'll notice even on the questions that I gave you on the previous page, not all of them necessarily are asking students to make a mathematical decision, and not all of them are necessarily asking them to consider the quality of the nature of the thinking that they're doing. So we really want to be conscious of that and make sure that when we do ask our students a question, we want to just take a moment and think ourselves about whether we've actually asked them to make a decision, or if we're asking them to simply explain why something happens or how it happens. That often they maybe have heard from somebody else and then they can just repeat it, or they may have heard from the teacher, or they may have heard from their parents at home. So we want to make sure that we're really ultimately getting them to justify and explain their reasoning in a way that demonstrates that they own that thinking. So think about that as you look at the questions that you use and how you use them in your classroom. And always remember, we want to do two things: engage our students in mathematical decision making, and secondly, really highlight the quality of their thinking. Not just get them to think, but get them to also be reflective and think about how well they're doing that thinking, because it ultimately leads to their success. Want to just very briefly talk a little bit about why thinking as sense-making. You can see here, these are just a couple of ideas, but really, as I said earlier, the ability to think is sense-making only if we really get to the quality of that person's thinking. So when we talk about, is something mathematically sound or reasonable, or does it make sense, we are really getting to the quality of the nature that they're thinking. And if we get our students looking at the quality of the nature of their thinking, and therefore being reflective, you can see that what happens is the students become very good sense makers. They know exactly what it means and how to go about doing it. It also ensures that they're engaged in ongoing self-reflection. And often what I like to talk about is self-reflection, but self-regulation, and really important in math, because I noticed a lot of your questions were about, what makes this right, or how do you know this is right? We want them to engage in that self-correction. It's really important to get them to stop and pause and think about whether something makes sense, or if it's not going well, is the answer right or wrong? Often in mathematics, I like to talk about how true do they believe the answer is, as opposed to whether it is right or wrong, because the study of mathematics is about truth. You can see here that it also nurtures skepticism. So it encourages your students to pause and say, I wonder if that really works that way. I wonder if after I've heard somebody's idea, I don't just simply applaud the idea all the time, but I pause and I take a moment and I wonder, is this making any sense? Is that reasonable? Is that sound? And this promotes effective and productive mistake making in our classrooms, and gets our students to understand that it's okay to make a mistake, because it's powerful. It's a really powerful learning tool, but it's only a powerful learning tool if they do learn to pause and ask themselves about, what about this makes it wrong? What about this makes it right? So sense-making is really also about meaning-making and developing understanding. And ultimately, it also nurtures fluency and automaticity. And we're going to see how these things play out in a moment as we look at some examples. Before we move on to actually looking at some math, I also want to cite something from NCTM, because the NCTM's written a number of really wonderful papers, but what I've cited here is a really short one that's easy to read. I think it's about, it's under 10 pages long, and it really gets to the importance of sense-making, and it talks about the relationship that I just mentioned, that sense-making is really closely tied and interrelated with mathematical reasoning. And mathematical reasoning is what gets students to understand whether they're engaged in good quality thinking. So you can see here they define mathematical reasoning as involving drawing logical conclusions based on assumptions and decisions, and we're going to see here that how that's related to a particular type of thinking in a moment. And they also talk about sense-making as involving an understanding of a situation, concept, context, and connecting it to other knowledge. So you can see here that the two are closely connected, because One is about meaning making, and the other is about knowing that that meaning making is actually true or accurate. And as you had said in your questions, is it right or is it wrong? I tend to like to stay away from the words right or wrong with my students because to them they feel like right and wrong means closure. And what we really want to do is ensure that our students don't believe that what they're doing in math classrooms brings closure, but it's inviting them to constantly reflect and think. You'll notice NCTM also suggests that there's a close relationship between these two concepts, but the really important piece around these two ideas, sense-making and mathematical reasonings, and how they're closely tied, is that it lays the foundation for all great mathematical thinking. So what I want to do is I want to give you some verbs to think about, and I want to ask you, and if you can use either a check mark or put a little marker on these words. Which of these words do you think require sense making? And I'd like you to just take a quick look, go through the list, and see if you can identify verbs. And these, by the way, are all verbs that come from a curriculum document. But which of these verbs do you think require your students to engage in sense making? I am so excited to see all of these question marks on this page and how really messy it looks. Because really what you're going to notice as we start looking at some examples is that sense making is connected to absolutely all the thinking that your students do in your classrooms. So covering this page with happy faces and check marks and a lot of these indicators that you're showing me on the page is really, really reflective of what we talk about as sense making being the foundations that lay all thinking in a mathematics, support all thinking in a mathematics classroom. Now that you've done that thinking, whether you checked off all of these or not, I'm going to ask you to very quickly, before I move on to my next slide and talk a little bit more about how foundational this is, I'd like you to just very quickly write down in the chat box, what do you think sense-making is? What kind of thinking is required for students to engage in sense-making? And just any thoughts that you have right now, because you've been connecting to some really important verbs here. So I'm sure that you're thinking about what the students need to do and how they work their way through doing these types of things. Okay, so I'm loving what I'm seeing. I'm seeing making connections, seeing patterns, making conjectures, estimating, changing your thinking, connecting to the real world. Wonderful. I am so excited because this says to me that you really understand that sense making is truly the foundation of all mathematical thinking. So I want to thank you for sharing all of those thoughts because they're really important for taking a look at considering our next slide. And what I'm introducing here is all the different types of thinking or reasoning that our students need to engage in order to be successful in mathematics. I'm going to contextualize this a little bit because this might not be, all of these might not be familiar with you as you glance at them because they don't actually come from our curriculum document. I'm going to show you on the next slide the connections, however. But what I want to do is tell you a little bit about where these came from, and this is really consolidation or a synthesis of research that I've been doing over about the last 5 or 6 years, and having looked at curriculum documents from around the world, different countries, different areas of the world, and also any post-secondary institutions, universities and colleges, and what they define as being mathematical thinking in their documents. And as a result of the synthesis of all of this work, you can see here that what has come out of that is what I'd like to talk about as 10 key thinking competencies, but the biggest one, and you can see here laying kind of a somewhat of a roof or an umbrella over all the others, is the idea of sound reasoning. And this concept here, the idea of sound reasoning, you'll see is connected to all the other different types of reasoning. So when I looked at your examples, I could see some of you talked about, changing your thinking, taking time to think about your thinking. That's reflective. A lot of you talked about how you're going to communicate things, or the use of symbols. Communicative, which also connects to structures. Is it done in a logical way, or how are you representing? Detailed-minded reasoning might be something that is new to some of you, I don't know, but it really came out in the research as being one of the really strong elements or key thinking competencies that are required for success in math. And often you'll hear about being detailed-minded as a habit of mind, but in fact the research suggests that students make decisions based on the number of details they have and having to fill in the gaps of the details they have, or even paying attention or not paying attention to details. So really important idea. Many of you connected to conceptual understanding or the understanding of ideas, a lot of connections, strategic thinking, and what's really interesting is what we tend to really see as kind of the umbrella competency as being problem solving. Problem solving actually sits somewhere here amongst all the other competencies, and we like to refer to it as, in the research, as problem managing reasoning, because we want students not only to be able to solve problems, but also to recognize them in their world, to be able to see those concepts at play and say, oh, I've got this problem, and I recognize that there's an element of this problem that requires mathematics to solve it. And that's what we talk about as being problem managing. I want to give you a moment and again ask you, just using a pen or a highlighter or something, do you see the connections here between what's on this page and the mathematical processes that are found in our curriculum documents? Do you see any alignment between the two, any similarities? And if you do, can you highlight them on the page? Is there anything in here that is similar or the same or connects very clearly to our mathematical processes in our curriculum document? So I'm seeing some highlighting around reflective. Now, what I'm hoping is that you're seeing that there is some overlap between the mathematical processes that are in our document and what the research is saying the 10 key competencies are for mathematical thinking. And what I'm going to show you on the next slide is a very clear connection. But what you can see here is at the top, sound reasoning is one of our mathematical processes, but according to the research, this process is actually the umbrella or foundational process that allows students to effectively do the other forms of reasoning or thinking. Probably what you didn't see, strategic reasoning, is being the selection of computational tools and strategies, and we want to teach our students how to do that in a very strategic way so that they're not just choosing or selecting those tools, but they're choosing them appropriate to context, situations, the alignment or fit to the mathematical ideas that they are doing, that they're considering and learning about. So a lot of different connections here. Interestingly enough, I noticed a lot of you highlighted conceptual reasoning, and I think that's great, but by the way, conceptual reasoning is not one of our mathematical processes in our curriculum document. However, many of you are probably spending time in your schools talking about how do we develop deep conceptual understanding. And we know from the work of Michael Fullen that this is a big focus in all our curriculum areas, but particularly in the area of mathematics, because mathematics is defined by concepts and ideas. And everything that we look at in math is actually a concept. And it's a concept that students need to understand and be able to construct meaning from. So conceptual reasoning really tied closely to that reasoning needing to be sound so that the students have a deep, accurate understanding, but also so that they are making meaning of the math that they're learning. I noticed that Jennifer's asked a question, what is meant by structural reasoning? So structural reasoning is where we get to how the students, because you see it's connected to communicative reasoning, and it's how students structure their responses when they communicate. And structural reasoning is really important in mathematics because we expect logical organization, we expect the correct use of symbols, we expect that mathematical ideas are written in a certain form. So structural reasoning is a little bit like text forms in literacy, if that helps make any sense of it, Jennifer. But it is really about how students structure how they communicate ideas in mathematics, because mathematics has very strictly defined rules and structures of how to communicate things so that they actually do make sense, so that they're actually clearly defined and generally acceptable, so that any mathematician who's reading what's being communicated both understands it very clearly and it makes it a universal language. So I hope that helps a little bit. But what's important here, and what I wanted to highlight, is how there is quite a bit of connection, like overlap between these ideas, but most importantly, that sense-making and sound reasoning is what really drives the quality of how students engage in this type of thinking and reasoning. I'm going to start off because I noticed that many of you, when I asked you what were you thinking about as you identified those verbs, I really loved the connections you made, and I loved the way you connected to the different forms of reasoning. But what's really challenging around understanding sense-making is to teach your students how to engage in good sense-making, to know how to do it well and effectively, requires that we think a little bit metacognitively, and that's always hard for many of us, and it's hard for our students, and that's why we really need to make that metacognition and what it is explicit to all of our students so that they all have access to this and are able to achieve success. So you'll notice here that when I talk about how do we describe the thinking behind sense-making, sense-making is a form of thinking, so this is how do we define the thinking behind thinking, or metacognition. And you'll see here that for any sound sense-making or reasoning, because I'm going to use those words interchangeably now because they are truly one or the same thing. The criteria for sound or reasoned or effective sense-making is making a mathematical decision or drawing a mathematical conclusion or solving a mathematical problem that identifies and assesses plausible options that do two really important things. Now, these are the two important things that we're going to take a look at really closely tonight. Anytime our students engage in sense-making, they need to be thinking about what do I already know and understand to be mathematically true about what I'm seeing, and what's all the information or all the clues or the details that are provided in the question of the task, because I need to engage in some detailed-minded thinking here, and so I need to make sure I'm paying close attention to all the mathematical evidence. And as students engage in sound sense-making, they are doing these two very specific things. They are making a mathematical decision that has them thinking about a lot of different responses that could take place that are all what we like to call mathematically plausible. In other words, they fit the context or the situation or the nature of the math that we're asking the students to engage in. And that as they do that, they're always thinking about these two basic foundational ideas. And this is what we call the metacognitive criteria for sound or effective sense-making or reasoning in mathematics. So right now, it probably sounds a little bit theoretical to you. So let's take a look at what that looks like in our math classrooms. And I'm going to apologize because I think that when the slides got downloaded into a Blackboard, they got a little bit skewed. So you'll notice the jars here are a little bit tall and thin, and they really shouldn't be looking that way. But I don't think that distortion is going to affect what I'm going to be asking you to do. I'd like you to consider the 4 different images here. And I want to propose something, and I want to propose that all good sense-making begins with a conjecture. And I want to start off, first of all, asking you just very quickly to jot down your ideas on what does it mean to make a mathematical conjecture. Are there any other words that you could use that could replace conjecture that you're familiar with? How would you define conjecture? And if you can just put some ideas in the chat box for me, that would be wonderful. Okay, so is there a theory to explain it? What's the hypothesis, an estimate? Hypothesis and estimate, great. Can you make a decision that's going to move you towards proof, prediction, educated guess? Okay, fabulous, great. So when we look at the idea of a conjecture, I'm going to pause just because one of the reasons what I like to have teachers share what they think a conjecture means to them is often what happens is I tend to see that nice little word guess starts popping up. And we have to be really, really careful when we use that word with our students, and especially with our really young students, because what happens is we tend to ask our students to make an educated guess or a reasoned guess or a guess that they can support somehow. And what we tend to do is encourage students to think that guessing is okay in math. And we really need to be careful around that word, because guessing really is probably the worst form of mathematical sense-making that we can ask our students to engage in. Because as many of you know, when I make a guess, the word guess, and if you have a moment, you can look it up on your phones or whatever, but when you make a guess, you're pretty much really not doing any thinking. You're saying whatever comes to mind right away. So you're making a very, very rushed decision. And what we don't want happening is that we have students rushing quickly to try to decide what it is that they should be believing, or what they think they should believe, or what they've heard others saying, so they think they should believe based on other people's opinions. We want them to stop and really take the time and pause and say, okay, what does this require? So when we talk about a conjecture, anytime we ask students to make a conjecture, we're really asking them to make a decision about something mathematical that is ambiguous. And I'm going to use those words for now, because what I would like to do is ask you to take a look at those 4 images again. You'll notice I've labeled them A, B, C, or D. And I'd like you to rank order them for what you think would require the easiest to the most difficult conjecture. So now that we have a good sense of what a conjecture is, if you took a look at those jars and what are in those jars, and we've asked the students to make a conjecture about the jars, and I'm going to let you think about what that conjecture would be, which of the jars do you think would be the easiest to make a conjecture about? And which of the jars do you think would be the most difficult? So I'm going to ask you to take a few moments and just pause and think. And if you would like, you could either list them in the chat box from most difficult to least difficult or easiest, or you can put them right on the rating scale that's on the page. So imagine that we're asking the students to make a conjecture about the nature of what's in the jar. Many of you have probably seen this, so you can probably imagine what the question is when we ask the students to take a look at what's in the jar. Which do you think is the easiest, and which do you think is the most difficult? Okay, thank you. And some of you have already started to answer what my next question is going to be for you. I'd like to ask, what made one more difficult than the others? So why did you choose one of those jars as most difficult, and what about it do you think made it more difficult than the others? Okay, so variation in the size. Okay, more items. So, okay, having a large number. Okay, so some of the jars you can see at the top, others you can't. Great. Wonderful. So I'm seeing a lot of inconsistency in size as being what makes it most difficult. So you've identified what I'd like to call a wide range of factors or consideration that might make one more difficult than the others. So if I take a look at all of these, because you've seen the ideas, hopefully you've had a chance to take a look at the ideas of others as well. Which of the following factors or considerations made it most difficult compared to the others? So if you were to highlight something, which one would you highlight? If you had to choose one of these, which would make it more difficult? Now I'm going to ask a very quick question of clarification. Did someone put a check mark next to the number of possible responses, or is that all around variation? Okay, great. Tell me a little bit about why. Why did you choose that? A lot around variation in item size and or shapes. Sorry, I'm trying to just take a peek here, make sure I'm catching all the ideas. So the variation makes it difficult to predict. Not being able to see everything makes it a little bit more difficult to predict as well. Any other thoughts? The more objects there are. So the smaller the objects, the size of the items, and if there's lots of them, it gets to be a little bit harder. Yeah, you can only see a few if you've got smaller coffee beans. The person who identified them, I don't know if you told me why yet, but the shape of the items, why do you think that's important? And if you'd like to jump in and just talk, that would be great too. What I'd like you to do now is, I really love the thinking that you're doing, and I'm hoping that you can see that the nature of the thinking that you're doing is the metacognitive thinking that we need to have our students doing so that they understand how they would make a conjecture, a sound conjecture about what it is that they're seeing. So really quickly to summarize, and I think this summarizes a lot about what many of you have said, is here are some basic reasons why one would be more challenging than others. Either the students don't possess enough, and what I'd like to call true or necessary mathematical knowledge to make the judgment. They can't access all the necessary details. They can't see it all. So notice when you're talking about different shapes, a lot of variation in the shapes, there's a lot of different shapes or variation of the shapes, or if the shapes are not simple or regular so that the students can clearly apply their background knowledge, it gets to be a little bit more challenging. And they have to start making some assumptions so that they can connect to what they already know and understand to be mathematically true. So you'll notice that that's the first idea here. The second idea, they can't access all the necessary details. You'll notice that all of these required a conjecture because I can't simply, some of you said this, I can't simply count what's in those jars. So because I can't see all the necessary details and have all the information, it requires me to try to figure out what's most likely rather than what is absolutely true, given the case. So the first one's about my background knowledge and understanding about what's mathematically true. My second one is about access to all the necessary mathematical evidence that I need to have. Okay? Now notice that sound reasoning, remember my definition of sound reasoning before, see how it plays in. It could also be a variation of the degrees of both. The one piece that I didn't see anybody, and perhaps correct me if I'm wrong, and please jump in and make a comment if you did say that, because I was reading the comments very quickly. I don't think I saw anybody saying, but there are so many possibilities. This is the reason why we really want to start all learning having students engage in a conjecture in our classrooms. Because if you notice here, if I ask you to make a conjecture, these are, very simply put, the criteria, the metacognitive criteria, that are required for students to engage in effective sense-making or sound reasoning. Let's take a look at the connections. Do you notice, remember I put this up just a few minutes ago, do you notice a connection between what's here and a lot of the ideas that you've shared? And I'm going to ask you to put up a happy face or a sad face. A happy face if you are noticing the connections and it's making sense, and a sad face if you're not, just so that I can see kind of where your thinking is at right now. Okay, I'm seeing a lot of happy faces, which is great. If I can't see something that someone's posted, I'd love to know if you have any questions at this point. If you don't want to show me a sad face, if there's something that you're wondering. And if you want to put that in the chat box, that would be great. If there's something you're wondering at this point. Rachel, are you able to use your mic? I'm curious about what you put in the chat box. Oh, it wasn't intended. You had me trying to make a conjecture. Okay, so I'm seeing a lot of absolutely connecting to prior knowledge. So one of the things that I want to have you thinking about as you leave the session tonight, when you go back to your classroom and you see students struggling around a concept, idea, well, let me say anything that they're doing in their math classroom, I want you to think about two things. I want you to talk to them a little bit about what they know and understand that they're connecting to. So the idea of background knowledge, and I often like to talk about existing or constructed background knowledge because often students don't possess it all. When I ask them to make a conjecture, I'm usually asking them to make a conjecture about something that they haven't perhaps been, they don't have all of the background knowledge that they need to have, because that's when they start making those really important predictions that they can now connect back to after they've engaged in some learning in my classroom. But I want you to go back to your classrooms and talk to the students who are struggling and ask them and have a conversation about two very important things. What background knowledge are they using, and is it in fact mathematically true? Okay, so when I say mathematically true, is it accurate? Or some of you might want to say correct. By the way, I use mathematical truth for a very specific reason for all children across all grade levels. And that's because mathematics is really based on truth, and it's really based on absolute truth. And often I want to get students to understand that it's not about the rightness of their response, but it's more about the fact that some things, well, I would say ultimately all things in math are about absolute truth. And that's something that is very different from other subject areas. I would say math and science are the two subject areas where that's really important. But I try to see if you can find out if they have any, in other words, do they have any misconceptions? So students typically struggle in two areas. One is they have misconceptions, or they don't have a full body of knowledge and understanding. Or two, they haven't paid attention to everything that's in the question or in the problem that's presented to them. And so what they tend to do is they make a rushed decision or a rushed mathematical judgment. And that's why I say we really don't want our students to be making guesses in our classrooms, or even encouraging guessing in our classroom, because guessing is something that I do very, very quickly. And it's not encouraging me to pause and stop and say, have I done these two things? Am I pulling everything that I know and understand to be mathematically true? And am I thinking about all the information or all the evidence or the clues for younger children, all the clues that are being presented in the problem, the question, or the task? Okay? So again, I want to highlight the importance of this criteria. I want to now look at what does it look like in some specific context. Now, I showed you the 10 key thinking competencies that students need to develop in order to be highly successful in mathematics. And I want to focus on, I'm hoping to get through 2 today, but I'm only going to focus on 2 because you'll notice that I did conjecturing, because conjecturing really lays the foundation of all good thinking in our math classrooms. And the reason why that's important is if I don't take a moment before I start solving a problem and ask myself, what is most likely the solution going to be, or what is the solution most likely going to look like? Is it going to be a large number? Is it going to be a small number? If I don't engage in that type of thinking, then I can't really engage in any sense making in my classroom, because I can't monitor my thinking as I move through all of my learning. Okay? So it's really important, and that's why I focused on conjecturing. I now want to focus on conceptual reasoning, because good sense making is required for conceptual understanding as well. And what I've done is I've given you 2 examples, and I'm hoping that you can see them okay. I've got them on separate pages. It kind of depended on what grade levels the participants in this session were, but since we crossed so many grade levels, I'm going to just leave this page up. And I'm going to ask you to take a look, and hopefully you can see clearly enough what's going on in both of these examples of student work. But I'm going to ask you to take a look and pick one of them and try to decipher what is it that the students do understand and what don't they understand. So in the first image, where the students are engaged in when the students engage in addition and subtraction, what is it that that student does understand? What is it that that student doesn't understand? And in the second image, where we've got a system of equations that are being solved using graphs, for those of you who are in the higher grades, grade 8 or up, what are you noticing that the student does understand and doesn't understand in that particular image? And I'm going to give you some time just to pick one of the pictures and just put your ideas in the chat box for me. And you can choose any one of these two pieces of student work. I don't need you to be thinking about both of them. Just choose the one that you're most comfortable with or you're most interested in considering. Okay, tell me a little bit about what you're thinking, because I'm not seeing any responses from anybody, so tell me a little bit about what it is that you're thinking as you're trying to work this through. And I don't need you to tell me what it is that the student does or does not understand. Just tell me a little bit about what you're thinking. Okay, so I'm reading some of the comments here. I apologize, I didn't see them earlier. Okay, so the student on the left-hand side doing addition and subtraction understands equality. The students can visualize numbers. Okay, great. Is there anything that you're noticing that the student on the left-hand side, with the addition and subtraction, is there something that they're not understanding? And it might be a little bit hard for you to see, so I'm going to flip it to the next page. Let's take a closer look. Is there anything that you're noticing that the student's not understanding, or there's not a clear understanding or enough evidence for us to see whether they understand this? So what I'd like to do is just highlight something small here. And this is as a teacher, the importance of detailed-minded thinking as well. When I look at this student work, there's something that, for example, if I look here and I've got two triangles and I subtract a triangle, I have one left. What do you think that one is showing, or does the student know what that one is showing? Okay, so I'm seeing someone just said sometimes the shapes are different. So over here, I've got 4 hearts plus 2 triangles equals 6. 6 what? And I think Rachel, you're asking a great question. Is the expectation that the student draw the shape? Do you think the expectation, if I want to know whether the student has developed good number sense, in other words, as they look at these numbers and they write these numbers down, do they understand what these numbers mean? Should I require them for these answers to be mathematically sound? should they be required to say 6 what? What are your thoughts? Should this student be saying 6 minus 4 looks like stars equals 2 stars? Should this student be saying 2 triangles minus 1 triangle should be saying 1 triangle? So the question is, have I been teaching about variables? Depends on your learning goals. So my learning goal here would be that I want to see that the students know how to add and subtract, but I would also want them, I'd also want to see whether they understand when they're adding and subtracting what that number means. So if they come up with their answers, do they understand what this number means? I'm showing you this particular image because I have to tell you, I was working, I'm working with a nonprofit organization in Peru, young children who are living in remote villages, so don't have really strong access to quality education. And the teacher gave them these sheets, and you know, all the kids were coming up to me and they were showing me that they're so happy that they think, you know, they're pretty sure that they got all the right answers. And they went through and they showed me, you know, like that, you know, they actually told me about how they know that this is a 2 and this is a 2. And they did understand their addition or subtraction, but what I noticed that they didn't understand is what the symbol of a number meant. And I just, every student that I talked to, I simply asked them, so can you tell me this is 2 what or 5 what? And they had absolutely no clue. So this said to me that the students really don't conceptually understand what it is that they're doing. Okay? This to me says, as I asked that question, it said to me that they really didn't understand what the meaning of these numbers were. And this is really, really important. So this is why I often say to teachers, worksheets are okay, but even if you're using worksheets, make sure that the students can communicate the meaning of what it is that they're doing. Okay? So the conceptual weakness here is that they don't really understand what all of these numbers are. And so when the teacher asked them to start explaining it, many of them couldn't. Many of them had the wrong answers. Many of them got confused when they saw 4 hearts and two triangles equals 6 what? That's really challenging. We're talking about kids who are in grade 1, and that's really challenging for students who are in grade 1, and they're saying, well, yeah, but wait a second, what is that number? And so the class had a really good conversation about that, but what I wanted to do is, I don't want to get too hung up on this conversation, but it's important that students are developing sound conceptual reasoning capacities. And so if I were to ask the students, this is 6 what, they should be able to tell me. They should be able to, using their conceptual understanding and their conceptual reasoning ability, saying, okay, as I look at what these numbers represent, I know that this should be a heart, or it should be a star. And if I'm not sure, then what am I calling these? See, like these here, when I've got hearts and triangles, this teacher's really asking that this child to understand that this number 6 just represents a generalized idea of a shape. And that's really challenging for children that age. By the way, it also skews their understanding of what an equal sign means and their understanding of equivalency. And for those of you who are teaching higher levels, there's a reason why when we get to algebra, we say things like, substitute in the following value for x to solve the equation, because really these things do possess a value. Okay. So I wanted to highlight that particular misconception and how conceptual understanding is so important. In this case, I don't know if any of you had a chance to actually take a look at the graph, but what's really interesting here is although a lot of this work is pretty good, it's a lot of procedural work, and this student really isn't understanding the concept of slope very well. It's a really foundational concept. And those of you who have an opportunity to take a closer look at this later, take a look at it and see why this student should have seen, if they're engaged in good sense making as they answered this question, they should have seen something does not make sense. Okay? And they should have been using those two criteria. What is it that I know and understand to be true? What is the meaning of slope that gives me these lines? And how do I pay attention to all the details? Where am I starting on the y-axis in order to create my slope? And does it make sense that my point of interception is going to be the 0.55, and why wouldn't that make sense? See, a student who's engaged in good sense making should have known and picked up that mistake as they were working on this. So I want to highlight that making sense of concepts is really critical, because ultimately we want to get our students to a point where, by the way, many of you are probably very familiar with the structure, the Freyer model, but we want the students to be able to create these representations, organize their thinking in the form of a Freyer model, but being able to do it on their own. So how do we empower them to do that? And we empower them to do that by teaching them very explicitly how to reason conceptually. What does that look like? So I'm hoping you can see this example. Okay, let me know if there's something that's not clear. But I want to ask you, what must the students think about to reason conceptually as they're completing this task? So here they've got what we call yes examples and no examples. I don't know if many of you are familiar with concept attainment as a thinking strategy. I'm guessing many of you are. Here the students have, on the left-hand side, a list of what I like to call true examples or yes examples of a concept, and then they have no examples to contrast the yes examples to in order to figure out what defines the yes examples. So what's the nature of the thinking that students need to do in order for them to construct an understanding of this concept, what it means, and then to be able to identify whether these two examples are both true or false examples of this concept. And you can see here that this is highlighted this highlights the concept of like terms. And I know not all of you are teaching grade 8 and 9, but to get to the thinking, I think all of you are probably able to do this. So if you compare the yes examples to the no examples, what's the nature of the thinking that you're doing? And again, I'm going to invite you to jot some ideas in your thought in the chat box. Okay, should we do it together just very quickly? If I take a look at the yes example, two terms, 2A and 5A is a true example of the concept. A false example is 2A and 2B. What should I notice? What will I notice, and what's the thinking that I'm doing? So I'm seeing, I'm going to see, okay, so different variables. So I've got two different variables in the no example, and so therefore the yes example of this concept of a like term, how would I define a like term? Okay, so I'm loving your responses, and I'm also seeing some responses telling, so I'm comparing and contrasting. Okay, so same variable. Great. So I've got some comparing and contrasting that's going on. I'm seeing patterns. I need to generalize those patterns. How do I do that effectively? So if I look at this, most of you said, if I look at the first example, I know that if this tells me that a like term has to have the same variable. Which is great. Notice I start with a very simple set of examples. What if I move to the next set of examples? What else does it tell me about a like term? So let me very quickly, because I'm cognizant of the time, let me very quickly tell you what the students will say. They compare the first two examples and they'll say, a true example has the same variable, but the number in front of the variable doesn't have to be the same. Okay? And that's when I, as a teacher, would say, by the way, that number has a name, we call it a coefficient. So you're saying that the two, and often they'll say the two letters, and I'll remind them that those two letters are variables. So you're saying that the variables have to be the same, but the coefficients don't. Does that still hold true when I look at the next set of examples? And the students will say, well, yes, I notice that the numbers in front, the coefficients, I'm going to remind them again, they don't have to be the same. They can also be positive and negative. They can also be fractions. But now I've got two variables, but they still have to be the same. Then they go look at the next example and they say, oh, I'm confirming my initial conjecture, and I notice that the variables have to be the same. But look at, I'm also seeing that the power associated with the variable also has to be the same. And they continue and they go through and they do that type of thinking. So many of you are saying, you're comparing, you're contrasting, you're seeking a pattern, you're generalizing that pattern. What's the nature of the thinking? All of those things, comparing, generalizing, seeking patterns. These are all the student engaging in sense making. As they do that, notice how we talked about, so what are these things? What do you notice? Let's call them things. The students are saying, what do I notice? What do I understand about what I notice as I compare? And so what do I notice? Have I been paying attention to all the evidence? And what do I understand and know about what I notice? And then they just test that again. So these are a series of conjectures, and you saw that earlier, those conjectures required those two metacognitive criteria. This is what we talk about as inductive reasoning. And then the students come up with a set of properties or characteristics, but mathematically I'd like to call them properties. They come up with a list of properties that define a like term, and then they're asked to take a look at these two examples, and these are quite challenging examples, and the students are asked to determine whether these examples are true or false. Are they an example of a like term or not? And notice it requires a justification. So as they're doing a justification, what do you think they're using in order to justify their response? Any thoughts from anybody in the group? As I'm deciding whether this is a true or false example, what am I using to justify that response? So here I've decided what a like term is, and I'm going to speculate the students are going to say that the variables have to be the same. Doesn't matter how many variables they have to be the same. Doesn't matter what order they're in, they have to be the same. But not only do the variables have to be the same, the powers or the exponents associated with each variable also have to be the same. So if I ask them, is this a true example, they're going to use those properties and apply those properties as criteria to determine whether this is indeed an example of a like term. This is what we talk about as being conceptual reasoning. Let's take a look at a simpler example. What is it what does the equal sign mean? In other words, what's equivalency? And again, I'm sorry, this is a little bit skewed, but these should be circles. And then so the students are given a true example and a false example. And they should be able to identify what makes this true and what doesn't make this true. Now, you'll notice that I create examples like this because the students can't just say it's dependent on quantity, because it isn't. Equivalency is not just dependent on quantity, it's actually dependent on value. Okay, so the students take a look at this, the children take a look at this, they're actually given these visuals, they're given some manipulatives that they can play with, they can recreate the representation, they build the mathematical vocabulary to do that, but ultimately they're going to say that this is true because the value of what I have on the left-hand side of the equal sign is equal to the value that I have on the right-hand side once I add them together. This is not true because the value of what I have on the left-hand side is not equal to the value on the right-hand side, because if I take a whole and subtract a half, it leaves me with a half. Okay, so the students then take the property of equivalency, and then they talk about whether these examples are true or false. And you'll notice that if we had time to play with these are really highly debatable examples. They're ambiguous, and it depends on what assumptions the students are going to make. What they do up here at the beginning is inductive reasoning. What they do to determine when they apply those properties as criteria, now they're engaged in deductive reasoning. In either case, notice the connection between the criteria, or what defines sound or effective or quality sense making, and the thinking that they have to go through. I'm going to give you a moment just to think about what I talked about, and I'd like you to tell me if you have any questions. Do you see the alignment between the nature of the thinking the students are doing and how this metacognitive criteria applies? I'm going to break it down a little bit. As the students are engaged in conceptual reasoning to arrive at conceptual understanding, and then they apply that conceptual understanding, are they making a mathematical decision? And if you think yes, just put yes in the chat box, or give me a happy face. As they're engaged in conceptual reasoning, are they making a mathematical decision? Okay, so I'm seeing a lot of yeses, I'm seeing happy faces. Are they having to consider a number, and I want you to think about, because I haven't gone through this completely for this, but when we did the like terms, are they having to consider a number of options or examples? And I'm hoping you're going to say, yes, they are. Are they having to use the following criteria? Are they taking a look at the yes example and saying, does it fit with what I already know and understand to be mathematically true? So as they're looking at the yes example here with the pizzas, they have to be able to construct, they have to understand what's going on in the image. If they don't understand what's going on in the image, if they can't connect to what they already know and understand to be mathematically true, they can't possibly reason conceptually. And secondly, does their thinking have to be consistent with the information and the clues that are provided? So this is what is really important for you to think about whenever students are engaging in this type of thinking. So I want to just highlight really quickly that in the first part of conceptual reasoning, their sense-making comes in the form of inductive thinking. So notice they have to consider a comprehensive and relevant set of examples. Now, the students don't always have to come up with the examples. Ultimately, as they become good conceptual reasoners, they're going to be able to kind of seek out the examples themselves and be able to say, okay, so I'm comparing all these different things, and I need to figure out what do they all have in common, and I need to assess them all to figure out what it means. I need to make sense of them. But in this case, with conceptual reasoning, often as the teacher, because this is where I bring in my expertise in the classroom, I want to give the students the examples, and they need to consider them and connect them to two criteria. So inductive reasoning is the students thinking about a relevant and comprehensive, a pretty full set of examples, connecting it to what they already know and understand to be true about the examples, and making sure that it's consistent with all of the information that is provided in the examples. Deductive thinking, they're now taking all of the different properties of the true or accepted meaning, and again they have to think about, is it consistent with these properties, what I already know and understand to be true, and is it consistent with all of the details or clues given to me in the examples? Okay. In both cases, the students are engaged in sense-making through conceptual reasoning. Now, this is really important, and I've introduced this example is as one of the ideas that I want to share, because I always want to start my learning with make a conjecture about something that you don't fully already know or understand or don't have all the details around. Because remember, that's the metacognition that I want to pull out. And then I want to say, okay, so if I don't fully understand it, or if my students are still struggling with a concept, or they don't have the necessary background knowledge, then I need to construct that understanding. And I construct that understanding through conceptual reasoning. And this is important because as they do that, students are able to do the following things. Without being able to reason conceptually, students can never clearly communicate the meaning of what it is that they're seeing mathematically. So think about the student who, gave the, 4 stars minus 2 moons is equal to 2 what? They can't communicate that clearly if they don't have that deep understanding. It won't allow them, they can't use their understanding and that meaning in a sophisticated way. They can't understand the significance, the importance of those concepts and relate it to ideas in their real world. And really, really most importantly, they can't arrive at new and better ways of explaining and representing those ideas. A handful of strategies that students can use in order to engage in conceptual reasoning is concept attainment, concept formation. So what you saw me sharing with you is concept attainment. Concept formation is when I give students a whole bunch of different examples, and I'm going to show you in a second, I ask the question, what do all these things have in common? Okay. Concept recognition is that deductive thinking. How do I know that this is the concept? And then I want to be thinking about meaning-making strategies. So let's take a look at an example before we close. Again, I apologize. Some of these images are skewed. But if you had a chance to play with them, you could probably see the connection between the two. I want to ask you to take a moment and think about, do all of the following representations belong together? And if you say yes, I'd like you to tell me a little bit about why. What are they representing? Okay, they all represent the concept of a half. That's a pretty abstract concept. Parts of a whole. Okay, are we sure about the one with the triangle? We're not sure about the clock because it's a different whole. It's a good question. It's a good thought. But it's still half of an hour. Okay, again, the concept of a half still being very abstract. Okay, I'm looking at a lot of different representations. What if I asked you to take each one of these and talk to me a little bit about, so if I look at the first image with the apples and the oranges, if I asked you, what do you see? What's the mathematical evidence? What do you know to be true about what you see mathematically? And then what idea or concept does this example show? How would this thinking help you truly see whether these are connected or not? So let's take the first example. What do I see? What's the mathematical evidence? Well, you don't have time to count them now because, and it's probably hard for you to see, but you'll see here in a very randomized way, there are going to be 25 apples and there's going to be 25 oranges. Okay, that's interesting, Nicole, that you're saying that there's 100 fruit. How did you get 100? Oh, 50, absolutely. So there's 50 fruit. So they're going to say there's 50 fruit. This is paying attention to all the evidence. There's 50 fruit or 50 apples and oranges together. 25 are apples, 25 are oranges. What do you know to be mathematically true about what you see? This is where I'm going to access my students' background knowledge. Okay, so the students are going to say, looks like 25 is half of 50. They're equal numbers. Fabulous. Half are oranges, half are apples. Notice now that when I say what idea or concept does this show, the students have already developed their understanding and they can talk about how this shows a half in a lot of different ways. What about the next one? Because there was a good question about the triangles. What do I see? What's all the mathematical evidence? Okay, so I see that 1/4 is shaded. Now, Nicole, I love that you've said that because this is where the students are, and because you're mathematically proficient, you're already jumping to your conclusion. Okay, so what are the students going to say? And this is where we have to get the students to pause and say, what is it that you see? What do you notice is in the picture? Because I want them to start paying a close attention to all the details in the picture. So tell me, what do you see in the image? So this is what I want to hear the kids say. I see that there's an area that is 5 squares wide and 10 squares long. Okay, so I want to see, or they'll say, I see that there are 50 squares. Great. I see that there are 2 triangles that look the same. Okay, I see that there are 4 other triangles that look the same. Okay, so now notice, I see that there are 2 rectangles that look the same. All right, if you're paying close attention to the details, what are you going to say about those 2 rectangles? Great, I see that one is pointing up and the other is pointing down. The same thing about the other 4 triangles. I want my students to start paying attention to all the details in the images. Okay, why? Can someone tell me why I want them paying attention to all those details? by the way, this is kind of what happens. Okay, so they can decide what's important. They can decide this by getting them to write down everything that they're seeing and paying close attention to all the mathematical details. That allows them to make connections between the math that they already know and understand. They're using all of their clues. Okay, so they're starting to pay attention to the dimensions of this geometric figure. The dimensions are going to be important because, notice, Nicole, you jumped right away to saying, well, I noticed that the shaded triangle represents a quarter. But not all of your students are going to be able to see that. Some of your students are going to be able to, but even those students, by the way, are not going to be thinking about the details that are going to help them support to justify that that's in fact true. Can you prove? Absolutely. Can you prove and reason that that's in fact true? If I pull together all the mathematical evidence and then I ask you, so what's mathematically true about that? See, the kids will start saying, well, the whole figure shows an area of 50 squares. Oh, that's really interesting. While the triangle shows an area of, so now the students are deconstructing, connecting everything that they're seeing so that they can arrive to accurate and true mathematical understanding. And once they've done that, then they can say, how big is that triangle? Is it a half? Is it a quarter? They can draw a conclusion that is mathematically sound based on everything that they're seeing, what they know and understand. They can draw that conclusion. Now, if you had time to do this for each one of these with these students, the students are going to start noticing that in terms of sets, 25 out of 50. In terms of the triangle, they're going to be able to notice what the size of that triangle is. Okay, so if this is half, so that the idea of this being a quarter, but what is it, like exactly what it is? What is the size of that triangle? It's going to be 1/2 the base times the height, right? And they'll be able to come up with that. If they look at the clock, and by the way, what's interesting about this is when I get my students to pay attention, then the students actually calculate the area that is shaded of the clock, because I can't possibly know if they all belong together unless I understand precisely what is being represented. Okay. I want to show you very quickly that when they move to the abstract number representations, now they understand what those numbers can potentially mean. They understand that these numbers are symbols that represent something. And they'll have the same, they'll talk about, so I see a 25, I see a line, I see over 50. What does that mean? 25 what? 50 what? What's that line mean? So many students have no idea what the line and the fraction actually means. They think 25 parts out of 50. Okay, but I want to highlight, so we use this in a fraction to represent something. What does it mean? So they have that conversation. Ultimately, I then want to throw something in here that's going to push their thinking even more deeply. Because now I've got 100 squares, and if this hadn't been skewed, you would have been able to see that the 100 squares that this circle solves within the clock is exactly the same size as the 100 squares of the 100 chart. But here I've got 50 over 100. Is that the same as the shaded area over here? Depends on how I interpret the number of squares. If I simply count the number of squares, so if I use the numbers, then I might say, oh, it's the same thing. It's 50 squares out of 100. But if I look at I see this as area, and I see that the half of this clock as area, then this is not going to belong. But again, I want to go back to the chart and now put that numbers chart in here and say, what do you see? What does it mean mathematically? What idea is being presented? Okay. Some questions that are here that help represent conceptual reasoning. I've just given you some samples, but what I want to highlight is that there's no type of reasoning that doesn't require this foundational type of thinking that is connected to sense making. Everything that your students do in your classroom, any form of thinking, requires sense making. And so I want to close by asking you, when we just saw these examples, just very quickly, can you see, can you highlight, did you see a lot of these things taking place, a lot of these different forms of reasoning taking place in what we did? And all we did was focus on sound reasoning and conceptual reasoning. But do you see the connections across all the other pieces? So I'm hoping that you're going to see things like, well, there was a lot of communicative reasoning going on. There was a lot of representational reasoning going on. There was a lot of connective. The beauty of focusing on sense making is it lays a foundation for all good thinking in your math classroom. I know we ran over a little bit. I apologize for that, and I hope that that's okay. But I want to bring it to a close here, and I'm hoping that when you get back to your classroom, you can really focus in on that metacognitive criteria around sense making that is so important and foundational to all math in your classrooms. I want to thank you for joining us this evening. Please feel free, if you want me to stick around for a couple of minutes, if you have any questions that you want to ask, I'm happy to address the questions if you put them in the chat box. You have my email address if there's anything that you want to, any questions that you have when you leave or you try to apply the ideas, please feel free to contact me. Again, thank you very much.
Okay, thank you so much, Laura, for this wonderful session of, as usual, of an extremely high academic level. Since we're running a bit late, I'm going to try to be really brief for my conclusion. I just want to quickly thank you all for taking time away from your families and for joining us over TF Connects tonight and for sharing your ideas throughout the session. And there was a lot of participation tonight and it was really, really wonderful. Now I just want to take a few more minutes of your time to talk about the upcoming sessions. Tomorrow evening, I'm moderating a French session for Jen Rochon. Kim, I noted that you are teaching French, so if you're interested or if you know some of your colleagues that may be interested, we still have some spaces left for tomorrow's session. The subject is not mathematics, obviously, but if you know French teachers or FSL teacher, please feel free to pass them my email address if they are interested. I'm just going to post my email in the chat box just in case. And that's mostly for Kim, obviously, because I know that Kim is a French teacher. There's also on March 28th, no, sorry, on April the 3rd, there's also a great session on mathematics by Marie-K Goindy. I've moderated for her, and she's really an exceptional moderator, so I definitely recommend that session on April the 3rd. And I also want to let you know that we have like 50 sessions coming up in April and May. I can't talk about all of them, but I'm going to post in the chat box the link to our calendar and to our resource page, and then you can go and explore. But there are lots of sessions coming up in the coming weeks. I also would like to tell you about an opportunity that is provided by OTF and the Ministry of Education. If you are a qualified teacher and you have completed an additional qualification course in mathematics, technology or kindergarten, you may be eligible for $450 subsidy, and I'm going to quickly paste for you in the chat box the link to our website that will allow you to apply for that $450 subsidy. That's about it. I just want to tell you that we welcome your feedback. For those of you who are new to OTF Connect, when you exit the session, you will be directed to a feedback questionnaire that we will ask you to fill up. It's very quick. And then when you are done with filling up that feedback questionnaire, you will be redirected to a survey, to a certificate of participation, and then you can add that certificate of participation to your resume, to your professional resume. So that's it. I just want to thank you all once again. Oh, sorry. You know what I'm going to do? I'm going to quickly paste in the chat box the link to the feedback survey and the certificate of participation, just in case you are not redirected. And I finally would like to thank you all and invite you to follow OTF on social media as well as on our OTF website. I'm now going to end the recording of the session, but please feel free to remain online if you want to ask Laura additional questions. Thank you once again for your participation in tonight's session, and we certainly hope to see you soon again on OTF Connects. Bonne fin de soirée à tous et à toutes, et merci beaucoup. Nous espérons vous revoir très bientôt sur OTF Connects. Au revoir.